So, our next talk will be given by Sophie Rehberg, and she is going to explain rational Ehrhart theory to us.
Yes, thank you. First of all, I would like to thank the organizers for this nice event that we are enjoying this week and for the opportunity to speak here. So this is joint work with Matthias Beck and Sophia Elia, and I will try to give a two-slide summary of what Ehrhart theory is, and then as a motivation to what's new, why do we do rational Ehrhart theory and what's happening there. And then in the end, I will give an example of a concept that carries over. I will talk more about this later. Okay, so we have seen Ehrhart polynomials a couple of times this week. Nevertheless, let me define them again. So we are thinking about polytopes. Those are convex halls of finitely many points in some space. Our polytopes in this talk are always full dimensional. And then we are interested in counting lattice points in those polytopes, so points with integral coordinates, and also counting them in any positive integral dilate of the polytope. And we define this counting function, this Ehrhart counting function that I've written there. And then here's an example, the unit square, and you can easily figure out that the counting function is n+1 squared. So that's a nice polynomial, and that's no coincidence. That's a theorem by Ehrhart from the 60s, that whenever you have a polytope with integral vertices, meaning all coordinates have integer values, then this counting function agrees with a polynomial of degree d. And that's why we call it Ehrhart polynomial, because it actually is a polynomial. And then you can generalize this to polytopes that have rational coordinates. And the counting function is still somewhat nice. It's a quasi-polynomial. And a quasi-polynomial looks like a polynomial, but the coefficients are now periodic functions. Yeah, instead of constant coefficients, we have periodic functions. And then we can give a bound, or can somehow estimate what the period of those, the common period of those coefficients is, by looking at what we call the denominator of the polytope. And the denominator is the lowest common multiple of all the coordinates of all the vertices of the polytope, right? So it somehow measures how rational are the vertices of the polytope. And then the period divides this denominator. Okay, and then of course, we want to do formal power series. Right? So we throw this into a generating series. And we can see that this is a nice form as a rational function. We know what the denominator looks like. And the denominator is called the H-star polynomial. That's again a polynomial with non-negative coefficients, with non-negative integral coefficients. Okay, so here's a crash course in how to compute the Ehrhart series for simplices. Yeah, we have this interval from 1 to 3. And what we do is we place the polytope in a vector space 1 dimension higher at height 1, and then we look at the cone over it. Yeah, so I've placed this interval, where am I here? At height 1 in this 2-dimensional space, and then I take the cone over it. And then in order to compute the H-star polynomial, the only thing we have to do is we look at this half-open fundamental parallelepiped spanned by the generators of the cone. And we look at the integer points in this half-open fundamental parallelepiped. And then this 0 point here gives us a constant 1. This point at height 1 gives us this t. And if there were, let's say, 3 points at height 2, we got 3 times t squared in this polynomial. Yeah, so we look at the number of points at each height. Okay, are there any questions so far? Let's take my two-slide summary of Ehrhart theory. Yeah, only in the interior, because we make it half open at the top, right? So those points are not included anymore. We take out the upper facets. Yeah. All right, so now I will move on to what we want to do now is, instead of only considering integral positive dilates of our polytopes, we want to consider rational dilates. Or actually, we can even consider real dilates. We will see that it doesn't make any difference. And of course, we were not the first ones to think about this. So there's a very nice paper by Eva Linke, who studied this counting function, and she already shows that this is a quasi-polynomial again, and that the coefficients are piecewise polynomial, and they are related by derivatives and many other nice properties. There's a paper by Baldoni, Berline, Köppe, and Vergne, who studied intermediate sums, and we can see this counting function there as a special case. And then Stapledon and some papers already introduced some kind of generating series approach, but he was counting integer points on boundaries of polytopes that always contain the origin. And we will also see that in the rational world, this will be a special property. Yeah. Okay, so let's get started with definitions. So we again define this counting function in the way you would expect it. Instead of taking integral dilates, we now allow rational dilates. And again, we could also allow real dilates. It doesn't really make a difference. So let's look at some examples. Very easy example, unit interval. We again place it in the space one dimension higher and look at the cone over it. And now what we one nice thing that I didn't tell you about this cone picture is that we can recover the polytope by intersecting the cone at height 1, right? And we can also recover dilates of the polytope by intersecting at different heights. So if I intersect at height 2, I get twice the polytope back. So now what we can do is, like, if we can intersect this cone at any height and see how many lines over integer points do we have in there. And that's what we actually want to count. Right? And then you can figure out we just need to take the floor function and add 1. And we can see this is a quasi-polynomial. It's a monotone function. That's everything we would expect. Okay, here's the second example. We take the interval from 1 to 2. And now things already get interesting. This is still a quasi-polynomial, but if you look closely at it, the original polytope contains 2 lattice points, 2 integer points, 1 and 2. If I now dilate it with a factor that's slightly bigger than 1, let's say 1.2, I will only have 1 integer point, right? You can see this in the picture here. If you go slightly higher, this line exits the cone. This one is in there, but the next one is not in there yet. So this counting function is not monotone anymore. And also, if you think back to the example before, it's just a simple translate, right? So I've just shifted this interval by 1, and it changes its properties. So that's something people who are used to classical Ehrhart theory, everything is invariant under integral translation. So I used to think about polytopes in terms of their shape and their size, but never in terms of their position. But here it actually really matters the position where the polytope is located. Okay. So now we are somehow stuck with this continuous counting function, but actually what we are doing is we are still counting discrete data, right? We still are counting integer points. So only at certain points when I dilate, something happens. Yeah, for some intervals, this counting function is just constant because, well, we need some time to reach the next integer points. And we can explain those intervals by introducing a new parameter that we call the codenominator. Let me explain what this is. So now we need to look at the half space description of the polytope. So every polytope can be described in terms of the intersection of half spaces, and that's this system of inequalities there. And now we want to say we only consider rational polytopes, so we can write this description with integer matrix A and an integer vector B. And then I also require that this description is in lowest terms, right? So every row of A and B together is in lowest terms. And now, since the polytope is also full dimensional, this description is unique. And then we can define the codenominator as the lowest common multiple of all the entries in B. And this is well defined. Okay, let's look at our examples again. Here's the half space description of this interval, and then the codenominator is 1. And for the second interval, the codenominator is 2. And this codenominator gives us the intervals in which this counting function is constant. And that's the first proposition here. So if we have a polytope this rational Ehrhart counting function is constant on open intervals from n over r to n plus 1 over r, where n is a natural number. And then if the polytope contains the origin, we've seen in the example, and it's true in general, that then this counting function is monotone, and we can close the interval on the lower bound. And that's nice. That's why we don't really care whether we want to do rational dilates or real dilates, because we only have to look at some intervals. And we are back to looking at actually discrete data again, right? And now we can define rational Ehrhart series and refined rational Ehrhart series. So for a polytope that contains the origin, if I want to know all the data of like every dilate, actually I only need to know the values of this counting function for multiples of 1 over r, right? Because then it's constant, and then I have the next multiple of 1 over r. And I can define a rational Ehrhart series by just using those data, and I will have everything, all the information that I need. And then if the polytope doesn't contain the origin, well, I need more data, right? I need the endpoints of all the intervals. So I still need all the multiples of 1 over r. And I need some value in this open interval. It doesn't really matter which one because it's constant. So we just chose the midpoint, because then we can write the refined rational Ehrhart series as like collecting all the data, like all the values for multiples of 1 over 2r. And then we have all the information that we need. Okay, so now let's study these Ehrhart series, these rational Ehrhart series. Here they are again. And here's our first theorem. We can again write them in a nice rational function form. Yeah. So we always assume P is a rational polytope of dimension D, so full dimensional. The codenominator will always be called R. And then we have one extra parameter that we call M, such that M over R is again a lattice polytope, meaning a polytope with integral vertices. And there are at least two canonical choices for M. I will talk about them in a couple of slides. And then we have this nice form. We have again a polynomial as nominator, which we call the rational H star polynomial, which depends on M. And it has again non-negative integral coefficients, but it is a polynomial in t to the power of 1 over r. So we now have fractional exponents, as we also might have in the denominator. Yeah. Okay, let's look at an example again. Oh, and we can do this again for the refined rational series as well. This will always happen. Whenever we know something about the rational Ehrhart series, we just replace r by 2r and rh star by double rh star, and the same things work. Yeah, it's the same, kind of the same thing. All right. Oh, yeah, I wanted to show you the proof because it's easy, and it tells us how to compute those Ehrhart series and Rh star polynomials, because you can just like reduce it back to classical Ehrhart series, right? So here's the definition of the rational Ehrhart series. And then what we do is we dilate by n over r, but that's the same thing as first shrinking the polytope by 1 over r and then dilating by integral parameters n, right? So we can rewrite this again and apply the classical Ehrhart theorem, and we get this nice expression. Yeah, so it heavily relies on the classical result. And that's how we can compute the rational H star, as we will see here in this example, right? So we've seen what we do actually is we compute the Ehrhart series for 1 over 2r in this case of the polytope, right? So in this case, r is 2. 1 over 2r is 1/4, so we shrink the polytope by 1/4, embed it at height 1, and then look at the cone over it. There's a different picture which I like much more because it's easier. We can just rescale this additional dimension, and then we get this picture, which is much easier to look at. And now we don't look at integral heights, but at heights that are again multiples of 1 over 2r. Right, and now we can read off the Rh star polynomial, right? So we have, here we are. We have one point at the origin, which gives us this constant 1. We have one integer point at height 1/2, so we get t to the power of 1/2. We have one point at height 3/4, t to the power 3/4, and one at height 5/4, and we get this. And that's it. All right, and then we can do like usual generating function knowledge, we can apply that here, and we can see that this counting function actually is a quasi-polynomial again, and we can again give an estimate on the period. It has a fractional period, j over r, and j divides m. Right? M was this parameter that we choose here so that m over r times the polytope has integral vertices. So in that case, we want to choose m as low as possible so that we get a nice bound on the period. So the smaller the period, the simpler the counting function is. So then we know like how complicated, we better know how complicated the function is. Okay, we can also do reciprocity, and those things were already in the paper by Eva Linke. We can recover this here. And we can also, in the case that m over r is again an integer, which is the second canonical choice for m, we can retrieve the h star polynomial from the rh star polynomial by just looking at all the summands that have integer exponents. Yeah. So here's the example from before. If we just take the summands with integer exponents, we are left with 1, and that's the classical Ehrhart series of this simple interval from 1 to 2. All right, are there any questions about this so far, the setup, the definitions, the series? All right, so now we have a rational Ehrhart series, and we can ask many questions from classical Ehrhart series, how they carry over in this new, like, refined world. And I want to show you this in the example of Gorenstein polytopes. I will define what they are and why they are nice, and then we will see how we can generalize this into a rational Gorenstein polytope definition. Okay, for that we first need the definition of what a Gorenstein cone is. That's a pointed cone where we can find a point so that if we translate the apex of the cone to that point, this new cone still captures all the interior lattice points of the original cone. And then this point is called Gorenstein point. Yeah, so you can see this in the picture here. You have this cone, and then you have this point here at 1, 1. And if we move the apex of the cone there, this new cone still captures all the interior lattice points of the original cone. And then we call a lattice polytope a Gorenstein polytope if the cone over the polytope is a Gorenstein cone, right? This construction of putting the polytope 1 dimension higher and coning over it. So why is this nice? Here's an example. Those polytopes, they have some dilate where we have a unique interior lattice point. And the h star polynomial of such polytopes is palindromic, meaning if I read the coefficients from left to right or right to left, it is the same thing, they're symmetric. Yeah. So here's this triangle, which is one example. And if you see, if you dilate it by 3, you get this bigger triangle with a unique interior lattice point. Okay, and now we generalize this to gamma rational Gorenstein polytopes, where we say, well, a polytope is gamma rational Gorenstein if the cone over the 1 over gamma times this polytope is a Gorenstein cone. Why do we introduce this parameter gamma here? Because we need to do this for r and 2r, and we can do this for other parameters as well. We are not sure whether this tells us something interesting, but anyway, it's easier to state the definition with some new parameter. But you can think of gamma as always being r or 2r. Yeah, and then it's easy to see that a lattice polytope is Gorenstein if and only if it's 1 rational Gorenstein, because if we replace gamma by 1, that's just the definition from the slide before. Okay, here's our favorite example again, and we can see it is 2 r rational Gorenstein, meaning here it's 4 rational Gorenstein, right? We have this point here where we can translate our cone, and this cone captures all the interior lattice points that we are interested in. And we can also see again that this RH star polynomial is palindromic. Well, here all the coefficients are 1, so it's a little bit boring, but in particular they're palindromic. And that's a general phenomenon. Yeah, so also for rational Gorenstein polytopes, we have this characterization. Yes, a bunch of them. So if we have a polytope that's R rational Gorenstein with this Gorenstein point, then this point gives us a unique integer solution to the system of equations. The RH star polynomial is palindromic. That's another way of writing it. This is a way of writing this in terms of the Ehrhart series or the counting function using reciprocity. And this last equivalence is actually well known in the literature. We just have it in the theorem because we need it in the proof. And of course, we can do the same thing again for, this was for polytopes that contain the origin, right? And then we can do the same things for polytopes that don't contain the origin by replacing R by 2R. And we get the same equivalences. Yeah. Okay. And we could actually write down these theorems for any L times R Gorenstein. We just don't think it tells us anything interesting, but it's possible. Okay, let's look at some examples again. Here's a different interval, slightly more complicated, from -1 to 2/3, and then the RH star polynomial looks like this. And if you stare at it for a moment, you can see that the coefficients are palindromic. You can also see that this is already pretty complicated for just being an interval in 1 dimensions. And it demonstrates a general phenomenon. Whenever we have the origin in the interior of the polytope, as it is the case here, then the polytope will be R rational Gorenstein with this Gorenstein point at height 1 over the origin. So this is again telling us the location of polytopes is very important, because in general, like in the classical world, a polytope being Gorenstein is a super special property. And here, all the polytopes that contain the origin in their interior, they are rational Gorenstein. So this is a super special property if a polytope contains the origin, because we cannot just translate polytopes. Okay, here's the second example you might recognize from a couple of slides before, which is this triangle, but now slightly bigger from 0 to 2. And this is actually rational Gorenstein. Now you can see this in this RH star polynomial here, but it is not in the classical world, because now if I dilate this polytope by an integer dilate, I already get 3 interior lattice points. Yeah, but there is some dilate that contains a unique interior lattice point, which in this case is, I think, 3/2, right? So then we get the same thing back. So with rational Ehrhart theory, we are able to somehow recognize that this polytope actually wants to be Gorenstein, right? It has a smaller dilate, which is Gorenstein, and we can see that here. And we can also see that, right, we can recover the H star polynomial from the RH star polynomial by looking at the summons with integral exponents. So this is actually refines this, and then it's symmetric or palindromic. Okay, but not all polytopes are rational Gorenstein. Here's an example of a polytope that's not rational Gorenstein. We've computed the RH star polynomial here. You can see it's far from being palindromic. And you can also see that in the picture. If you dilate these 2 interior lattice points, they enter and exit the polytope at the same time. So we will never have a unique interior lattice point. All right. So now we can, as I said, look at many other questions that we know from classical Ehrhart theory. For example, it would also be interesting to look at what does it mean to be reflexive in the rational setting. In the classical world, reflexive, the Gorenstein polytopes are a generalization of reflexive polytopes. Reflexive polytopes are those that contain a unique interior lattice point. And then if we look at the polar dual, this polytope is lattice again. And they have a bunch of other interesting properties. But it's not so clear how to do this in the rational setting, because those properties do not always coincide. There might also be connections to the fine interior of lattice polytopes. This is also a way of defining, like generalizing the notion of reflexive. There's also a bunch of generalizations of reflexive polytopes already. And really, we can ask any other Ehrhart theoretic questions about unimodality of RH star polynomials, log concavity. We've heard these things. All right, thank you for your attention, and I'm happy to answer more questions.
Thank you very much. Are there questions?
Testing. Okay. Thank you for that lovely talk, Sophia. It's always exciting to hear you speak. Do you know this last point you said? Any other Ehrhart theoretic question? Have you all thought about symmetric decompositions of the rational H star?
I have not, but Esme Bajo and Matthias Beck have. They recently posted a paper about symmetric decompositions, where they also consider the rational H star. So there's a paper on arXiv where you can read about this. Yeah.
Another question?
Hey, thanks for the talk. So maybe a basic question, but like when you talk about the cone, you use this Hom notation. So is there some connection to algebra there? Like, is this the same as the Hom set from algebra?
It's also called homogenization, because if you look at the description in terms of the intersection of half spaces, you will get a system of inequalities where the right-hand side equals to 0, because all the hyperplanes then go through the origin. So it's a way of homogenization of your system of inequalities.
Cool, thanks.
So for some rational polytopes, you can still have a period collapse. That means that you still have a polynomial, Ehrhart polynomial. So that's something you can detect with your rational H star polynomials.
Thank you so much for this question. I have an extra slide for this because we also thought about this question. So let me get everybody on the same page. Period collapse means whenever we have this upper bound on the period by the denominator, and whenever we actually have a smaller period, we call this period collapse. And this is a very weird phenomenon that's like not really clear when it occurs. And here are 4 examples that show that apparently there's no relation between integral period collapse and rational period collapse. So here's one classical example where we have integral period collapse, but no rational period collapse. Here's a recent example from a paper where we have integral period collapse and rational period collapse. Here's a simple example where we have no integral period collapse, but we have rational period collapse. And in this example, there's no period collapse at all. So yeah, we were also hoping to see something there, but we have this kind of non-result.
More questions?
Might just be nothing, but one of your examples had 1 minus t cubed in the denominator. And I just noticed that if you wrote it as if you wrote numerator and denominator as a polynomial in t to the 1/2, that then you have cancellation. Is that something that generalizes? So you just get 1 over 1 minus t to the 1/2 cubed.
Yeah, this somehow boils down to the question or to the detail of how we choose this parameter m. Right, there are several choices of choosing m, and I think here we chose m in a way that m over r is an integer again, because then we can recover the h star polynomial. But you could reduce this expression. Yeah, this expression is highly non-unique. It always depends on this parameter m.
Okay, thank you.
So no further questions. That seems to be the case. So thank you very much again.